integrating n choose x between negative infinity and infinity. Let's go. So we're going to use this identity n choose x plus n choose x plus 1 equals n plus 1, it's not over, n plus 1 choose x plus 1. So this is kind of wacky. We can prove it though, and it's not too tricky. So we're going to want to write them in factorial form. So, and also this identity applies in with the gamma definition for binomial as well. So we have n factorial x plus 1 factorial, and then we have n minus x plus 1 factorial. So I'll just say that's x minus 1 factorial. Okay, so we want to put this in a common denominator. So we see we have an x plus 1 factorial here, we have only x factorial here. So if we times the top and bottom by this one by x plus 1, then we will get this. We'll have x plus 1 factorial on the bottom and n minus x factorial on the bottom as well. Now, similarly for the other side, we have an n minus x factorial here, but n minus x minus 1 factorial here. So we times the top and bottom by n minus x. Then now we can add these together nicely. So adding these together, and we can also sort of factorize out that n factorial straight away. We have x plus 1 plus n minus x. X plus 1 factorial n minus x factorial. And you can see here that these x's cancel out on the numerator. So we just get n factorial, lots of n plus 1, which can be rewritten as n plus 1 factorial. So we have n plus 1 factorial on the top, and x plus 1 factorial, n minus x factorial. And this is just n plus 1 choose x plus 1. So there you go, that's the identity all proved nice and nicely. So, okay, now we've got that, let's actually do the integral. So we're going to say I of n equals the integral between negative infinity and infinity of n choose x. So this is what we are looking for, right? Now, interestingly, if we make this x plus 1, this is essentially the same as just shifting the integral, to the left by 1, right? But since we're integrating between negative infinity and infinity, that translation isn't actually going to matter, and it's not going to affect the actual result of the integral. So we can say that this integral is the same as n choose x plus 1 dx. So if we add these together, we have 2in equals this integral of n choose x plus n choose x plus 1 dx. And using our identity, we can say that 2in equals integral of n plus 1 choose x plus 1. So yeah. So, and you'll notice this is actually the same as I of n plus 1. So we have 2in equals I of n plus 1. So we could say that I of n equals 2 lots of I of n minus 1. Okay, so you can see that if we sort of expand our I of n minus 1 again, we get 2 lots of I of n minus 2, and then we get 2 lots of I of n minus 3. This is going to keep going until we reach 0. So you can see that I of n equals 2 to the n lots of I of 0. So if we can work out what I of 0 is, then we're done. So let's try that. So I of 0, we have the integral between negative infinity and infinity of 0 choose x dx. Okay, so when we're actually doing the integral, we are going to have to move away from the factorial definition, and we're going to have to use the gamma function, because the gamma function is defined for all real x, whereas factorial is not. So I'm going to start by quickly saying the gamma of x equals x minus 1 factorial. So I of 0 equals integral to negative infinity and infinity, yeah, gamma of 1 over gamma of x plus 1 gamma of 1 minus x dx. And so what we're going to do now is, I'm going to say I of 0 equals, and gamma of 1 is just 1, so we're going to have 1 on the top, and we can rewrite this gamma here as x, lots of gamma of x. So you can see this is 1 over x gamma x times gamma 1 minus x. And this allows us to use the Euler reflection formula, which is gamma of x times gamma of 1 minus x equals pi over sine pi x. Okay, so now we have I0 equals x to infinity to infinity, and now we have sine pi x over pi x dx. And now we can do a u sub for pi x. So say u equals pi x, du equals pi dx. So I0 equals 1 over pi, integral between negative infinity and infinity of sine u over u. And this is just the Dirichlet integral. So this gives us pi over pi, which is equal to 1. So we know that I of 0 equals 1, and I of n equals 2 to the n lots of I0. So our answer is just 2 to the n. There you go.